Welcome to the deep dive.
Yeah.
Today, we're tackling a really persistent challenge in AI sequence modeling, for things like text, audio, time series data.
Right. It's this constant balancing act.
Exactly. You've got these really powerful models like transformers. They're amazing at context, right? Any part of the sequence can look at any other part.
Yeah, fantastic for understanding relationships across the data.
But the problem is the compute cost. It just explodes. Quadratic scaling means as your sequence gets longer, it gets really slow, really expensive. So analyzing a whole book or a long audio file, not ideal.
And then you have the other side, the linear RNNs, recurrent neural networks. These guys process data step by step.
Much more efficient.
Way more efficient for inference on long sequences, thanks to that linear scaling.
Right.
But the history there is they've struggled with expressivity. They weren't so good at tracking complex state or remembering patterns over really long distances.
So there's this classic trade-off, efficiency versus power.
Pretty much.
Okay, so the core problem we're digging into today, and this comes straight from the research you shared, is how can we sort of boost the power, the expressivity of those efficient linear RNNs? How do we make them genuinely good at handling complex state and long dependencies without losing that crucial linear efficiency?
Well, yeah, researchers have been poking at this for a while. They've tried different things with the state transition matrix. That's the core part that updates the model's memory at each step.
Right.
Some recent models, Mamba, GLA, they use fairly simple matrices, like diagonal ones, super efficient, but maybe limited in what they can learn.
Okay.
Others, like DeltaNet or RWKV, they tried more complex structures, often diagonal plus a rank 1 update. It gives them more power, definitely, but they hit their own trade-offs, which, we can get into.
And that brings us nicely to today's focus, DeltaProduct. The source material really presents this as a promising new way to handle this whole expressivity versus efficiency puzzle.
Yeah, it's a clever approach.
So our mission here, especially for you, the listener who wants the technical details, is to unpack the innovation behind DeltaProduct. And we want to get to those aha moments, understand how it works and why its design gives it these unique capabilities. All right, let's get into the core innovation. The source material explains DeltaNet's update process in a really interesting way. It's like taking one tiny step of online gradient descent for each token.
Right.
And the matrix it uses is this thing called a generalized householder matrix. Now, that might sound a bit technical.
It basically means it's mostly an identity matrix doesn't change much, but with a specific tweak. It's I minus beta times K transpose. And K is like a direction vector.
So it does a kind of reflection or transformation along that direction, scaled by beta.
Exactly. That's the DeltaNet baseline, one transformation per token.
Okay.
And here's where DeltaProduct takes that leap. Instead of just one of those steps per token, it says, okay, what if we do on each of them?
Multiple steps.
Yeah. So the state transition matrix for each token isn't just one householder matrix anymore. It's the product you multiply together, NH different generalized householder matrices. Each one looks like JT, and you multiply NH of them for each input value.
So this number, NH, the number of these householder matrices you multiply, that becomes the main control, like a dial.
Precisely. That's the elegant part. It's a tunable parameter. By changing NH, you can smoothly go from being just like DeltaNet when NH equals 1, all the way up to creating much richer, more complex state transitions. When you multiply these specific I beta KKT matrices, the result has this nice structure. It's the identity matrix plus something else that has a rank of at most NH.
Rank meaning its complexity.
Sort of, yeah. It's a measure of how many independent transformations it can really do. So NH gives you very fine-grained control over the mathematical power of that state update. It neatly connects the number of these conceptual gradient steps to the matrix's expressive capability.
Okay, that makes sense. But why does multiplying them make it so much more expressive? What can it do that a single one can't?
Good question. So remember, a single householder can do reflections, right?
Okay.
Especially if beta is around 2. It can flip things, give you eigenvalues like mechan 1.
Right.
But products of householders, they can do much more. There's this theorem, the Cartan-Dieudonné theorem, which basically says you can build any orthogonal matrix, think rotations, reflections, things that preserve lengths by multiplying enough reflections together.
So that's the analogy, right? Like reflecting something in one mirror, then reflecting the reflection in another mirror.
Exactly. If the mirrors aren't parallel, the end result is a rotation.
Got it.
And that intuition holds mathematically. With DeltaProduct, if you use NH2 householders, for instance, and their K vectors aren't aligned, their product can actually perform a rotation. This shows up as the resulting matrix having complex eigenvalues.
Complex eigenvalues? Okay, so not just real numbers like +1 or -1?
Right. Single householders or standard orthogonal ones only give you real eigenvalues. But DeltaProduct with NH greater than 1 can generate these complex pairs. That's crucial because it allows the model to perform rotations within, say, a 2D subspace of its hidden state.
Which is a much more sophisticated transformation than just scaling or flipping.
Absolutely. Being able to model rotations lets it capture things like cyclical patterns or much more intricate state changes over time. That's where the expressivity really gets a boost beyond simpler models.
And the source material backs this up with some pretty solid theory, right? Theorems 1 and 2.
Yeah, they provide some significant theoretical guarantees. We don't need to wade through the proofs, but let's talk about what they mean.
Yep.
First, group word problems. These are tasks designed to test state tracking. Imagine tracking permutations, like shuffling a deck of cards that's the symmetric group SN delta product can solve any of these group word problems.
And any of them. That sounds powerful.
It is. Now, how it solves them depends on NH. If you set NH high enough specifically, at least N1 for the group SN, it can solve it in just one layer.
Wow. Okay.
If you use a smaller NH, say greater than 1, it might take 3 layers. If NH is 1, like DeltaNet, maybe 4 layers. And these multi-layer solutions might need a little help, like a lookup table in one layer. But the point is, increasing NH gives you options, fewer layers or maybe a smaller lookup table. It adds architectural flexibility for these tough state tracking jobs.
Makes sense. And the second guarantee.
Regular languages. These are patterns you could recognize with a finite state machine, like checking if an email address has the right format. The paper shows that gated delta product, that's delta product with an added forget gate, pretty standard in RNNs, can recognize any regular language, given a finite number of layers.
How does that work?
Well, the intuition comes from something called the Krohn-Rhodes decomposition. It basically says any finite state machine can be broken down into components that do permutations and resets. The householder products in DeltaProduct, great for modeling the state permutations, and the gate, that handles the resets. It maps quite nicely.
So compared to other models, how does DeltaProduct stack up theoretically? There was a table in the source, right?
Yeah. Table 1 compares capabilities. The upshot is, with NH1, DeltaProduct shows improved theoretical expressivity over the original DeltaNet. For certain tasks, up to 3 layers, it even looks better on paper than models like RWKV-7.
Like that S5 word problem.
Exactly. Being able to solve the S5 word problem, which they show in Figure 1, theoretically places it outside a complexity class called TC0. Think of TC0 as simpler counting operations. Being outside TC0 means it can handle more complex stateful computations, similar to RWKV-7 in that regard.
Okay, but here's something really crucial you mentioned earlier, stability. How does DeltaProduct handle that? Because RNNs can sometimes, blow up on long sequences.
Right, that's a huge challenge. And this is a key design feature of DeltaProduct. The source highlights that the state transition matrices it generates always have a spectral norm less than or equal to 1.
Spectral norm.
Yeah.
That's like how much it can stretch things.
Yeah, roughly. Keeping it at or below 1 is a mathematical guarantee that the hidden state won't explode no matter how long the sequence gets. It ensures stability during training.
How do they guarantee that?
It comes from the properties of those generalized householder matrices. If you choose the beta parameter correctly between 0 and 2, each individual householder matrix has a spectral norm of exactly 1. And a fundamental property of norms is that the norm of a product of matrices is always less than or equal to the product of their norms.
So multiplying things with norm 1 keeps the results norm at most 1.
Precisely. It's built into the structure.
That sounds like a big advantage. How does it compare to, say, RWKV-7 then?
Well, that's a key difference. Models like RWKV-7 actually relax this constraint. They allow their state matrices to have a spectral norm greater than 1.
Why would they do that?
It gives them flexibility. For example, they can represent a copy operation more directly, which technically has a norm of square root of 2. This might let them recognize some regular languages in fewer layers. The source mentions 4 layers for some cases.
But there's a catch.
There's a potential catch. As Theorem 7 in the source points out, allowing norms greater than 1 can lead to instability for certain model weights or inputs. The recurrence might blow up. So DeltaProduct makes a very specific design choice. Prioritize guaranteed stability by strictly bounding the norm, even if it means potentially needing more layers or a larger NH for some tasks compared to models that risk instability.
Okay, so it's a conscious trade-off.
There.
Guaranteed stability versus Potentially faster computation on some tasks at the risk of instability.
Exactly. It's a core part of DeltaProduct's philosophy.
All right, so the theory sounds really compelling. Richer expressivity, the rotation capability, solving group problems, guaranteed stability. But does it actually work in practice? Let's look at the experiments. First off, that state tracking stuff. They tested it on those permutation groups, S3, S4, A5, S5. What did they find?
The results were pretty striking. Figure 5 in the paper shows performance as sequences get longer. The key takeaway is that increasing NH going from 1 to 2 or more dramatically improved how well the model performed on sequences way longer than the ones it saw during training.
That's length extrapolation, right? Super important.
Critical. And interestingly, they found that just increasing NH was more effective for extrapolation than simply making the model deeper by stacking more layers of standard DeltaNet, which is NH1.
So adding those extra householders per step really paid off there.
It seems so. And for S4 specifically, the results were really cool. DeltaProduct with NH2 performed so well, it strongly suggests the model learned to exploit that connection. We talked about S4 being structurally the same as the rotation group of a cube.
It actually learned the rotations.
The evidence points that way. It seems to have used its 2 householders per step to mimic rotations in a 3D subspace. They even looked inside the trained model. One head consistently used beta values near 2 for both householders consistent with reflections, and the direction vectors, k vectors, clustered nicely in 3 dimensions when they applied PCA. You can see that in figure 7. It's a nice case of the theory playing out.
Very cool. And they also mentioned something about the eigenvalues.
Yeah, figure 12 suggests that keeping the eigenvalues in that sweet spot between naitic 1 and 1, which the bounded norm helps with, was important for getting good performance on these state tracking tasks. It reinforces the stability aspect.
Okay, what about language modeling? Moving from abstract math groups to actual text.
They tested it on datasets like CodeParrot, Trivia QA, some math problems. And again, looking at perplexity over sequence length, figure 8 shows there was a really sharp improvement going from NH1 DeltaNet to NH2. Performance was still great at NH3, holding up well even on very long sequences where other models might start to degrade.
Why do they think it works so much better there, especially on long sequences?
Their hypothesis is it has a better forgetting mechanism. They looked at something called effective rank. Over time, think of it as measuring how much distinct information is stored in the hidden state.
Okay.
What they saw in figure 9 was that some parts of the gated DeltaProduct model seemed to load up information at the start of a sequence, but then they could reduce this effective rank, essentially clearing out old state much more quickly and effectively than DeltaNet when new information came along. This better state reset capability is probably key for handling long texts with different topics or contexts.
That makes intuitive sense for language. Okay, last piece. Scaling. How does it hold up when you try to make the model bigger and more powerful?
They compared 2 strategies. Strategy 1, increase NH DeltaProduct's way. Strategy 2, increase the hidden dimension size within each head, the standard way to scale DeltaNet. Figure 10 shows the results. Scaling up by increasing NH generally led to better improvements in training perplexity, and DeltaProduct maintained its performance edge on downstream tasks as the models got bigger. It suggests that scaling via NH is actually a very effective, maybe even preferable way to increase the capacity of this type of architecture.
So adding more structure via householders seems better than just making the state vectors bigger.
The results point in that direction, yes. And crucially, they mentioned the implementation builds on DeltaNet's efficient parallel scan. So the actual runtime, the throughput, scales linearly with NH. That's figure 4. So you get more power, better scaling, with a predictable compute cost increase.
Okay, let's try and wrap this up for everyone listening. The big idea with DeltaProduct seems to be using that product of householder matrices controlled by NH.
Right. It's not just arbitrary complexity. It's a very structured way to dial up the expressivity. It directly tackles that efficiency versus expressivity problem we started with for linear RNNs.
And we saw this structure gives it real theoretical power solving any group word problem, recognizing any regular language, the ability to perform rotations.
And maybe most importantly for practical use, it does this while maintaining that guarantee of stability because the matrix norm is always kept less than or equal to 1.
Which then translated into practice, showing much better length extrapolation on both the hard state tracking tasks and on language modeling compared to the simpler DeltaNet baseline.
And the scaling experiment suggests that NH is a good lever to pull if you want to make the model more powerful.
So thinking about the academic contribution here, it feels like they've found a clever way to build more mathematical structure and expressive power into the state transition of a linear RNN while keeping it stable, really pushing what these efficient models can do.
Absolutely. It's a solid piece of work in making these linear models more capable for challenging long sequence tasks.
Okay, so here's a final thought for you, the listener, to mull over. We spent some time on that trade-off DeltaProduct makes. Guaranteed stability, normally it's 1, versus the approach of models like RWKV-7 that allow norms greater than 1, potentially getting more direct power for some things, but risking instability. What does this tension tell us about the ultimate limits of stable linear RNNs? Is there an inherent ceiling? Can a linear recurrence be arbitrarily expressive if it must stay stable forever? Or could there be other tricks, other ways to get the benefits of those higher norm operations while somehow, cleverly, maintaining that overall stability guarantee? It really feels like this interplay between stability and expressivity in these efficient sequence models is still an active and fascinating research frontier.